It looks simple. Let's see what it looks like graphically. All right. So these are my two observations: the height and the weight. And I have some children represented by black circles and some adults represented by red circles. So what does this estimation look like geometrically? What it looks like is first I compute the priors, right? The prior for the child and for the adult, and then I start estimating the height. Right? And what that means is I have all of these individuals in 2D space, right? I'm just looking at the x-coordinate, the height at the moment. So, and I'm not looking at all of them, I'm just looking at the children, the black dots. Okay. So if I do that, effectively what I'm doing is I'm just projecting the points onto the x-axis. So that's what it would look like, right? So there is one child who is really, really tall, right? There is one child who's really, really short, actually quite a few really short children, and then there seem to be a few children with exactly the same height, which could happen in the data. So that would be the histogram, and once I compute the mean and the standard and the variance, I am effectively modeling that histogram with a Gaussian. Right? As you can see, it's not a very good fit. Right? But then again, I don't have very many points, so I don't know if it's a good fit or not. And I am going to be using a Gaussian, so this is, that's as good as it's going to get. I've got my mean, I've got my variance. It's not going to get any better unless I use something other than a Gaussian for this case. So that's the height. Now I do the same thing for the weights. Again, project all the children to the y-axis, get a histogram, compute the mean and the variance, and from the mean and the variance, man, any second now, I'm gonna get a Gaussian, right? Okay. So I have my for the children, I have the Gaussian for the heights and for the weights, and then these Gaussians are independent. As part of a naive Bayes classifier, remember, I'm multiplying together these probabilities. So effectively, in space, geometrically, what it's going to look like is I'm multiplying, I have a Gaussian on the x-axis, I have another Gaussian on the y-axis, and I'm going to do a cross product of them. I'm going to multiply one by another. And what that looks like is I'm going to have a bump in 2D space that is axes aligned, right? It can't be turned. And it's going to sort of have big numbers around this area where both the height and the weight have big probabilities, and we'll have decaying numbers. So imagine sort of a bell popping out of the plane straight at you. That's what this Gaussian looks like. So that is my model of the children. That's it. It consists of a product of a Gaussian for the heights and a Gaussian for the weights. Then I do the same thing for the adults. I get a Gaussian that might look like that, right? And then what happens next is I get a new observation, and I ask myself a question: is that observation more likely to come from the model of adults or the model of children? So maybe that is my observation. That cross is the new individual. I don't know if that is a child or an adult, and I want to predict it based on these two models. So how do I do that? What I do is that individual has a height and a weight. Those are the only two things that I'm considering. So what I'm going to do is I'm going to plug him into the equation of the Gaussian for the height and the weight and see how likely am I to see this height and a weight from a child, this height and a weight from an adult. So that's the equation for a Gaussian. H of x, that's the height of my new individual x that I've never seen before. So I'm going to take that height, subtract the mean height of children, square the difference, divide by the variance of the height in the children, take a half of that and raise e to that power, and then multiply it by effectively a constant. So that's the part that you always have in a Gaussian. Okay. Now, so we're not going to compute that. But you can look at the picture and make some general inferences about that, right? So if this is the individual, and these are my models, is this number going to be a big number or a small number? Okay, so I'm hearing small numbers. Who thinks it's small? Who thinks it's big? We're taking the height of that individual, So the height is somewhere around here. Subtracting the mean height of children, and where's the mean height of children? It's right here. Right? So does that child's height, does that individual's height look like an average child's height? Yes. It actually looks dead on. So this individual has the same height as an average child. So what that means is that this quantity is going to be 0. 0 by anything is going to be 0, and then you have e to the minus 0. That's going to be 1. Right? So I'm actually looking at a pretty big number. That individual has a height that looks a lot like a child's height. It falls smack in the middle of the Gaussian distribution for children's heights. So this is actually going to be a big number. Now, what about this one? This is the probability of a weight, assuming that you're in the child class. Okay, big number, small number? Small number, yay. So it's small because his weight is actually really, really high. It's a lot higher than the expected weight of a child. So the probability of observing a child with that weight is pretty small. That's what that number represents, right? So I do it for the child class, then I do it for the adult class, and again I get two numbers. So that, big or small? Small, yay. So this guy is kind of short for an adult. So his height is a little bit small, and the weight is going to be big because the weight is right in the middle. Okay, so I get these four numbers: the probability of height and the weight under the child class and the adult class. Then I'm going to combine them, right? Because remember, this individual x, it's represented by two parts: the height and the weight. So probability of x given the adult class is going to be probability of the height given the adult times probability of the weight given the adult. So I'm just multiplying them together. That's the naive part of naive Bayes. Then I'm going to do the same thing for the child, and then I'm going to combine them using Bayes' rule like that. So probability of this individual being an adult, probability of adult given x, is probability of that observation, that part given the adult class, normalized by the overall probability of that individual.